Well, all right. Here it is, our third or fourth video of the day. How fun is this? So section 11.1, so chapter 11, we get into functions of multiple variables. Okay? Something like this, I don't know, x plus y, or some similar. Okay? I like to think of it this way. Again, I always like to go back to statistics. That's kind of a neat way of doing it, I think, personally, but you do you. Like, my blood pressure is a function of my weight, maybe, and the amount of exercise. Whatever it happens to be. Okay? And it's that idea that these two guys both have some impact on z. Okay? Pretty straightforward, pretty easy to do. So a couple things to think about. In the past, we talked about domain as being the allowable values of x, but that's not true anymore. Okay? So in the case of this, z is our dependent variable. X and y are our independent variables. So our domain then, be careful. So check this out. Like for instance, if I do this, z is equal to 3x plus 2y minus 7 or something like this. Is there anything that x and y can't be? And the answer is no, no. So just x and y are elements of, now you can do this a couple different ways. You can say R2, okay? That is anywhere in the two-dimensional plane. You can say it like that. You could say that x is between there and there, and y is between there and there as well. That makes you happy. A couple different ways to write it. Don't really care. Just want you to think about it. That's the big deal to me. I want you to think about what they can be. Now, if it was something along this line, say now, what? Well, yeah, here's the deal. So this case, because they're in a squirt, as always, you cannot square root negative numbers, friend. 0 or greater is what we're talking about. So we know that this inside function, you see, must be greater than or equal to a goose egg. Yeah, that's interesting. I feel like that gives us this thing. And I feel like that is, my friend, a circle, you see, with a radius of 3. So anywhere in here, that is the domain of my function. Okay? Excuse me. Now, you're like, well, do another one, Jay. Do another one. Okay, I will. Interesting. Very interesting. Interesting. What do we know here? Well, I feel like the denominator can't be 0, but I also feel like that could probably factor that guy. What do I know here? X had better not equal y, otherwise we got a problem. Wait, that means this is the line y equals x. And in our, so that's looking down at the xy plane. We cannot be, now you're like, is that a plane or is that a line? Well, listen, anywhere on this line in the xy plane, we can't be anywhere on that, regardless of whether we're up above it or not. It doesn't matter. In other words, you cannot have the point 5, 5, something is not going to work. That does not exist because they can't equal one another. Okay? Same things have always been true. Can't divide by 0. Can't square root a negative. Can't take the natural log of 0 or negative for that matter. Natural log of I don't know. There you go, right there. Sure. I don't know. All I know is that this thing here better be bigger than 0. Straight up bigger than 0. Okay? Because otherwise we got a problem. Well, that means that x had better be then greater than, I don't know, y squared minus 2. Wait, what does that look like? I don't know. Check it out. Boom, boom, boom. I think it looks like this. And x's had better be in here. Can I graph that, Jake? Can you show us how to do it? Sure. Go to desmos.com. Desmos.com. Yeah, I feel like I've been. Now you're like, oh, that's x equals J. It is. I know. It wasn't supposed to be equal. It's supposed to be greater than. What? No, you didn't. So everywhere in that red region would be our domain. I don't want to belabor the point. It's pretty straightforward. Again, it's the same thing we've done in the past, just kind of taking it to a different level. Now, the part that I do want to kind of belabor the point about is to talk about, well, what kind of situations. Now, obviously, I talked about, things like statistics. Obviously, that's true. But, there's other things in our daily life that actually work this way. So, for instance, we talked earlier about centripetal force. Well, actually, centripetal acceleration. Well, let's do a centripetal acceleration. Let's do that one. Is equal to v squared over r, or if you prefer, if this makes you happier, v squared times k. And this is just, of course, this is the magnitude of that stuff. Okay. So what am I saying here? Well, what we're saying is this: is that and I want to go with the radius if you don't mind. Okay. So if this is my z here, and this is my x and my y, what I've got going on is this: is what happens to z as r gets smaller. Okay, well, as y gets smaller, what happens to z? This z gets huge. That's right. And vice versa. As y gets big, z gets small. That's true. And what happens as our x gets big? Then our y gets really big in a hurry, or z rather gets really big in a hurry. And likewise, that's also true if it's negative. In fact, let me just pretend for a minute. Let's pretend. Let's just look at this and let's just go, wait a minute now. Let's let y equal some constant value. I don't care what it is. Just pretend with me, okay? Just let it pretend. Let's just pretend, man, okay? What is that going to look like? Well, this then would look something like, and just go with me on this. Y is a constant. Could it be a half? Sure. Could it be 5? Sure. But what I know is it's going to be this. It's going to look something like this guy. And if you were to look on the z versus x plane, what would you see? Why, you'd see parabolas, wouldn't you? Are you with me? They'd be parabolas, and they'd be steeper or fatter depending on what c is. Yes, and you're like, could they be negative? Well, yes and no. In our case, no, because we're talking about a radius, obviously, so that can't happen. But in another situation, sure, I suppose they could be negative. And so viewed from this side, they're going to look different based on what c is. For instance, this might be when c is equal to a half or something. This might be when, or what have you. Are you with me? They're just different values. And what this is called the xz trace. In other words, let's just pretend that we've held, in this case, y constant. What's it gonna look like if I'm looking down just the zx plane? Okay. What it's like is like coming along to a particular value of, in this case, y, and chopping the function off and then looking at what's left. And then moving to a different value of y and making another cross-sectional chunk out of it. Okay, now you're like, okay, that's neat. Do another one. Cool. So then what if I said, well, let's let x equal a constant? Then this really becomes z is equal to some constant over y. Well, I'm no dummy, but I am a dummy. I don't know. Listen, I feel like it's going to look like this. They kind of look like this. They will change based on what c is. Now, interestingly enough, there's a couple ways to do this. If you wanted to sketch them out, a fella could do them in here like this. Now, you have to be a little creative because Desmos can only graph in terms of y and x. So let me just demonstrate what I'm talking about. So on that first one, let's just let y equals, okay? And then, what was the first one we did? It was cx squared, right? So then what a guy can do is put it like something like an a and then x squared. And then you can add a slider. And, get out of there. You can add a slider. Go away. Nobody wants you here. And you can see that all you're doing is that changes. In other words, that a is like our c value that we talked about a few minutes ago, right? And the idea is, in this case, y is our z value because I can't really do it any other way. And you can see what's happening here. As you change that value of c, y, you're just going to get a bunch. Viewed from this side, you're just going to get a bunch of parabolas. That's all you're doing. That's it. That's all you're going to get. And then you're like, well, what about the other one? All right, I'm glad you asked. So if I did y, sorry, I'm just dying today. I went for a walk and I come back and I feel like I'm catching something. I just always feel when I come inside. Just sound like I'm dying over here. I'm gonna die. Now, like, Jay, you were right. They are those little hyperbolas over there in the first quadrant. Well, I am right. You're right. But note that it's also over in the third quadrant? Kind of, right? Kind of. In our case, our x was x squared, right? C was like what x squared was. Are you with me? And so obviously that's going to be positive. So what I see over in this third quadrant doesn't really happen. It's just going to be a bunch of those guys. Now you're like, well, that's cool. What does it actually look like on a real graph? Well, I'm glad you asked. So what the guy can do is come over here and go z equals, right? And just go in here and just punch it in. Oh, I know what the problem is. Maybe if you used your keyboard, it would work, dummy. Ah! X squared divided by y. And kaboom. What? Now, no way. Now, no way. Hey, look, viewed from this side, what do you see, friends? Viewed from this side, I see a parabola. A bunch of parabolas. In fact, if you spin around down this end, you might even see them better. Oh, more parabolas. All right. Now you're like, well, some of them are negative parabolas. Again, in the real world, we weren't allowing our x's or y's to be negative. Boom. So we're only looking at this aspect over here. And in fact, apparently, we're cutting off part of it. Because, oh, no, tell you what, yeah. So x can't be negative 2 either. So it really only is this piece here. But it's a half a parabola. And then again, viewed from the side, what do you see? You can see them coming down, can't you? You can see in a three-dimensional world, but you can kind of look at them. You're like, hey, I see those hyperbolas that you had drawn for us a minute ago, right? Over here on Desmos, wherever Desmos went. Right there. See these hyperbolas out in here? Whee! And they change like that. What? That's the same picture. Okay, those are the x and y. This would be the z, x. I'm sorry, not the zx, you dummy. The zy trace. Okay, now you're like, oh, that's kind of neato. Now, back in the day, it's not actually. It is kind of cool. What I think it's helpful to do is to visualize, because in this chapter, we're going to be doing derivatives. And specifically, we're going to talk about partial derivatives. And that's the idea of clearly x and y are going to have an impact on z. The idea of a partial derivative is how much of the change in z is coming from x and how much of it is coming from a change in y. Okay? Well, if I know what that function looks like, in other words, if it's a parabola, I know what parabolas look like. The derivative of a parabola is, x squared, that is 2x. And I understand how that piece works. So in parabolas, it just gives me a kind of a heads up as to how this is all going to play out. Now, you're like, okay, well, that's kind of neat, I guess. What about, is there an XY trace? In fact, there is, and this is the most important one. And in fact, you've actually done these before. And you're like, no, I haven't. Oh, yeah, you have, friend. Yeah, you have. So, for instance, check this out. Suppose I said, and I'm just going to leave it as this x squared over y business, right? I'm just going to leave it this way. Let's let z be constant. What do you mean, Jay? Well, what I mean is this. When I look at this guy, what I think to myself is, I feel like when I do this, if I look down on the xy plane, I should be able to graph out some sort of a region where everybody on this line, everyone on this line, which is a bunch of x's and y's, if you will, right? Has the same z. And everyone on this one would have the same z, and so on and so on. You're like, oh my word, topo map. Yeah, topo map is a very good explanation for this. So when you're out wandering about in the woods, there's a lot of places that have the same exact elevation. You're exactly right. Hey, what about the weather map, Jay? Hey, I'm glad you asked that. I hadn't thought of that one. No, yes, I had. Hey, look, there's a high pressure system or a low pressure system. These are iso bars, right? Everywhere on these bars will have the same pressure. Ooh, cool. What about, apparently the U.S. looks different now. Whatever, don't really care. Hey, look right here. Look, 80 degrees, 90 degrees. What? Oh, look, these are isotherms. Okay, we've done all manner of stuff like this over the years, right? There's lots of different ones of this. This is, as I say, the most important one. And so what we end up calling these guys, we either call them level curves, or another name for them is, I hate when my brain goes dead for a second. Level curves, and come on, Jay, pull your head out of your backside, you idiot. Level curves and contour plots. And I didn't even have to look it up. As soon as I pulled the book over, I was like, duh. Now, mathematically, we will call them one or the other. Typically, this guy. And as a matter of fact, no one is going to make you draw them by hand. Yes, back in my day, which was not the good old days, you're welcome, we had to sketch these by hand. And it was not fun. It was not fun. At all. Not even a little bit. No, sir. Not cool. Okay? It was a giant pain in the buttocks, to be quite honest with you. Okay? So, in this case, this one isn't terrible, because a guy could, for instance, simply do this. If you let z be a constant, why, then this really becomes x squared over c. And let's be honest, this looks like what? This looks like a parabola, yeah? Again, it looks like a bunch of parabolas. And so everywhere on these different parabolas will have, so for instance, this one here, this might have a z, which of course is equal to c, might be something like 7 on this guy, and so on and so on and so on. Okay? And so that's not terribly difficult. It's just a question of how do you pull that off? And well, here's how you do it. So a couple ways to do it. You can come in here, this little red doodad right here, click it. And then what you can do is you can have it start, in this case, at -1 if you want to. That seems goofy because none of our numbers are that small. I don't think I want to start at -1. I'm going to start at 0, thanks. And I'm going to count by 0.2, and I'm going to have 11 contours for grins, I guess. And I hit create plot. There it is. And oh, look at that. It's as if Mr. Groom knows what he's talking about. What does it look like to you? Looks like parabolas to me, friend. That's exactly right. Now, what? If you touch it, it does that, doesn't it? Yeah. What did it do? In other words, it superimposed those levels, you see, on the actual side of the curve. And you're like, oh, that's kind of neat. Yeah, I guess. It is what it is, you know, whatever. So let's get rid of this fella. Let's do a different one. So let's put in a z equals again. Let's just make one up here. So let's just do one here that looks cool. I'm going to do a little 3x times, oops, I don't know what I just did there, times the sine of y plus y. Nice. What? Look at that. What? That's crazy. And let's go from -2. Let's just go from -12, shall we? Let's get out there a ways. Have some fun, huh? Let's do it, man. I got this. You got this. Oh, mercy. Now I get changes up here, too. Nice. And notice it's clipped. Notice that it's clipped off right there. So I'm going to go a little higher. I don't know how high I need to go. I wasn't really paying attention to myself when I did that. Apparently higher still, but you get the picture. Nice. What? Very interesting. Very interesting. Very interesting. Now, let's close out of this thing here. Close, go away. So again, we have 3x. I shouldn't have gone out as far as 12. I shouldn't have done that. Let's just go out to 6 maybe. The reason I'm saying that is, of course, this one has no limit on its bounds in terms of its domain. Now, the reason I did that is just let's get in here a little tighter and we can look at it. So, what do we got? So, you got 3x. So, the sine of y, obviously, is going to be somewhere between -1 and 1. This is going to go up to a maximum of about 18. Plus, we can be adding 6 to that. So, about 24 is the biggest we're ever going to get on our z values. I'm going to go ahead and put them up to 24. I'm going to go down to -24. The idea here is we're going to get in a ballpark that we should be capturing them. Oh, notice they're clipped again. That's part of my issue. Nice. Oh, yes. Mucho better. Nice. Nice. There you go. Cool. Whatever. Now, like viewed from this side, you're like, what the heck is that goofy thing? I don't know. Viewed from this side, you can kind of see it might be a sine wave, and it might continue out there for a while. What? So what I want to do is I want to take a look at this thing here, and let's assume, first of all, let's talk about our domain and our range here. So we had z is equal to 3x sine y plus y. Anything y can't be? No, nothing y can't be. Y can be anything it wants to be. Okay. So y is an element of the reals. Okay, and x is also an element of the reals. If you prefer, you want to say that it's between 0 and infinity, knock yourself out. Makes no difference to me. Now let's assume that y is constant. So then what I see is I just see 3x times some constant value, because the sign of y, the sign of a constant is going to be a constant, plus a constant. So what this looks like an awful lot to me is it's some constant times x plus a different constant, because 3 times k is a different constant than just regular k, if that makes sense. What does this look like? Well, viewed from this side, the z versus x side, what I'm going to see, I think, is a bunch of lines, and they're going to change slopes on me, because as x, I said that's not true. They're not going to change slopes. They're going to change. They are going to change slopes, and they're going to change y-intercepts. Because if I choose a different value of k, some of them are going to have steeper slopes and a different y-intercept, and some will have shallower slopes and, of course, different y-intercepts. The idea is it's going to be kind of linear in this case. In other words, so as x increases, z increases linearly. Does that make sense? In other words, because y is not really changing in this case. We're holding y constant. Very similar to whenever you do an experiment, typically you want to hold one variable constant and manipulate the other one so that you can see what effect that has. So we're saying let's let y stay put, and we're going to only manipulate x. Well, if that does it, then as this goes up, look, that's a constant. That's linear right there. You see that? It's linear. And so as x goes up by, let's say, 1, if x goes up by 1, then z is going to go up by a. That's a linear relationship. Now, let's look at it the other way around. So let's let x be constant. So you get z is equal to 3 times a constant, let's call it a, sine y plus y. Interesting. I wonder what the sine of y plus y looks like. We should go look. I'm just going to do sine of x plus y, but sine of x plus x, rather. No, it's going to look something like that. Interesting. In other words, it's going to continue to kind of cascade up as we go. Well, now you put a 2 in front of that, or a 3 in front of that, or something. It makes it steeper, obviously. Nice. And in fact, if you go and look, is that what we see in our picture? Yeah, kind of. You can see it kind of stepping up as you go that direction, can't you? You see it? It's going up, down, up, down. It's going to continue going up and down as we go. There's our y right there, and z, of course, is up here toward the top of this thing. Okay? And that's great. Now, if you spin it the other way, so the x is over here. If you look, I see, it's kind of hard, it's kind of tricky to see it, but you can see you've got lines. If you look at them, they're like it looks like a V, but it's really lines. And it depends. Could you end up having a negative slope? Sure. That's why some of them are going downhill in this situation. Okay. Now, again, it's just a way of picturing what's going to be happening with our function. Now, guy just comes in here like so, closes that, close it, hits the old contour plot. Now, you can do it a bunch of different ways. You can change this up a little bit. You want to count by 0.5s. You knock yourself out. Sweet. Boom. It takes a minute. It thinks. It whirs. It does its thing. Kaboom. There you go. Okay. And pretty straightforward. And like Jay, but some of them were negative. That's right. Some of them were negative. So guy could do something like this. Hey, let's start at negative 10. Hey, let's count by 1s. And let's go 11 of them, I guess. Well, that's not bueno because I'm only going to go to 0. Let's get 20 of them. What do you say about that, huh? 21 of them. What the heck? Boom. So now I'm going to have positives and negative values. Give it to me. And so there you go. Listen carefully. I do not want you to attempt to draw these on paper. Okay, so on the homework, I want you to be able to look at them and identify what's going on. Okay, I want you to be able to see that. And we're going to use these guys for some pretty cool things later on. Okay, we're going to use them to help us determine where some maxes and mins lie, where some things called saddle points lie, and some other things of that nature. I want you comfortable with them. Okay, for heaven's sakes, I'm not going to ever ask you to sketch out a drawing. It's never going to do that. That's just ludicrous. I have better things to do than have you guys do something like that. Oops, here, let's redo this. I'm just going to go ahead and click on this normal one here like that. You're like, yeah, sure, give me that, whatever. Boom. Come on. Oh, I thought I hit enter. Maybe I didn't. Click it, you hippie. Oh, fiddle faddle. Oh, now I pissed it off. Sorry, don't get angry at me. Don't hate me. Don't hate me. Here, reset. Oh boy, she's angry now. I'm sorry. Sorry. Okay, there we go. So I push the button just once. It's thinking about it, I think, maybe. Gosh, okay, today would be good. Make me a contour plot. Oh, fiddle. Okay, well, I didn't really want to do that. Thank you for that. That was wonderful. How about we just reset? One more time. All right, are you going to work this time? Okay, what I want you to see is that just like on a topo map, when they get concentric circles and they build up, that's either going to be a maximum or a minimum. Always, 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 always true. So in the case of the first quadrant, that's clearly a maximum. And the third quadrant is also a maximum. Okay. And then, of course, down here in the fourth and the second quadrant, those are obviously negative, or the minimums. What happens at the origin? Well, interestingly enough, this would be a situation where if you're coming toward the origin from over here at 1, 1, well, let's not say 1, 1. Let's say, what was that, 0.2, 1 or something right here in this maximum area. If you were, oh, fiddle. Anyway, if you're wandering down this direction, I'm over here on the contour plot now. If I was wandering toward the origin, down into here, as I move down into here, like so, what's happening? Well, I'm getting lower and lower and lower on the graph, but then I head back up the other side. Cool. So it's as if it were a maximum. Not so fast, friend. Because if I was coming from this way, I'd be going uphill. And then downhill again. And the idea is that going this direction, it looks like a maximum. Going this way, it looks like a minimum. We have a name for that. It's called a saddle point. Okay? And so we'll use this idea of a contour plot quite a bit in the future for several things, one of which is to help us determine whether we have a max or a minimum or a saddle point. Those are the three main key features. And we'll do it other ways too, but it's always nice to be able to go back and double check. Does that make sense? Oh yeah, that makes sense. Sometimes you only have that. Something else that we can use it for is for actually approximating the volume under a surface, and we'll talk about that more later on. And because that's that idea of you're using that to approximate the heights. So if you knew what the areas were, you could find the volumes. And we're going to talk more about integrals in chapter 12, but not terribly difficult. Okay. Again, it's pretty straightforward. I was going to do a couple of example ones here just for a good time. Oh, one other thing that we'll use them for is, and you know this if you've ever used a topo map. Okay, if you look on a topo map, let's actually do that, shall we? Let's look that up. Let's look up a town that's somewhere, yeah, I don't know, Dixie, Washington. I used to farm out by Dixie, Washington back in the day. I grew up just outside of Waitsburg, Washington, at the Dayton High School. That's great, Jay. Nobody cares. No, I know. So here's a game. And what the heck just happened? Why am I not on a Giggles? Oh, I forgot. My stupid Google Map's not working properly. Oh, I got to use a stupid edge. One moment, please. While I go to Google and do this instead. Brother, Dixie, Washington. Boom. Boom. Tiny, itty bitty little place. Live way out in the sticks. But as you know, if you go to Giggle Maps, you can click on the terrain feature. Oh, nice. Jeez, Jay, look at all the hills. That's right. That's right. Yep, we farmed on these hills up in here. So, as you can tell, obviously, where is the water run? Well, the water runs, if you zoom in on some of these guys a little bit, it's going to run down these draws like so. Yes? Hey, does the water run down there? You sure does. Why? Those are the fastest ways down the hill. Okay, why is that? That's because that's where the contours are closest together. And then later on, we're going to be talking about that in terms of looking at things and going, oh, which direction will be the fastest way down the hill? And we'll talk more about that when we get there as well. Come over here and check this out. That obviously is a maximum, right? You can follow everything up the hill. This is probably the steepest way to the top of that hill, right? By the way, that's where the direction the water goes, obviously. And there you go. Bunch of different places up in here. No big deal. I lived up in here somewhere. Kind of hard to see it, but yeah. So yeah, good times, good times. And kind of interesting in terms of, you know, following where the roads go and where they live. So I live down in, where did I live? Down in here somewhere, yeah. Anyway, yeah, farm some of these big old hills up in here. These big old nasty knobs. But again, the idea is you're very comfortable with topo maps. That's right. So look at that. It's 2,400 feet everywhere along this line. It's 2,600 feet everywhere on this line right here. Sweet. Hey, look at this. What is this? There's not much of a swell. This right from here down into here is a gentle down and then gentle back up the other side. Sure. Hey, look, this is climbing and then back down. This is a saddle point. Nice. In fact, my grandpa and some of them guys would actually call it like up there in that saddle, right? And you're like, all right, cool. And to me as a child, you're like, oh yeah, saddle, because it looks like a horse saddle, because it did. And yet, that is why it was described that way probably back in the day. Whoever was doing the math described it that way as well. Hey, it's a saddle point. Okay, this would be a maximum, obviously. I don't see any true minimums in this neighborhood because everything kind of flows down on all these creeks. Same idea though. Okay, and so again, pretty straightforward. But we're going to use this idea of level curves quite a bit in the future to approximate, which direction things will flow. We use a thing called the gradient vector later on, which is pretty easy to do, and it's actually pretty powerful. So it's kind of a neat thing to do. Okay. In this section, I also want to just mention this: if you had a contour map of elevation. Like so, and this was the highest point up here. High, low, nice. Stop it. Go away. No one likes you. There you go. But clearly, if you're the water, you'd want to head down, and you'd always want to be crossing these guys in a perpendicular fashion. Okay? So that's why it's going to tend to bend, try to cross these guys always perpendicularly. Why? Because that's going to be the steepest path down the hill. It's going to bend and turn, so it's always crossing in a perpendicular fashion. And then when it gets down here, it's going to get a little weird. It's actually going to kind of wander this away, looks like, and cross down in here somewhere when it's the closest between the two. Now, it's going to have a weird little bend in its leg here. Why? Because it's not steep right here. This is pretty shallow. It's not steep at all, right? It's kind of flat. So it's going to peel. Oops, what are you doing? I don't know what just happened. Apparently, I leaned on a key. It's going to wind this direction quite a bit, but it's going to cross it in a perpendicular fashion and then head toward the other one again in a perpendicular fashion. Always looking for that. So we're going to be looking as we go along. And again, that's part of what we'll talk about when we get to the gradient vector. That will tell us which direction we should be traveling at any point in time. Now, in section 11.1, I don't actually want you at all. I don't want you to do any of the sketching of the graphs. Does that make sense? It asks you to sketch them and whatnot. This is not 1985 or even early 90s. What I want you to do instead is I want you to use the graph, the 3D calc plotter. I want you to feel comfortable with it. You don't need to print them out. Just do them, okay? So don't get weirded out by that. Now I'm going to do something in Excel, and I'm going to put in some numbers here. I'm just making them up, so don't get all weirded out. Like, where'd you get the numbers from? Just made them up, dude. Whatever. And I don't know, some different numbers going down the side. Whatever, okay? And I could make up some, these are my X values across the top, these are my Y's, let's say. I could make up some Z values, I could do that. Or I could put in something like this. I'm just gonna make up a function here. I'm gonna go 2 times this guy. And you don't need to really pay attention much to what I'm doing in this regard. I'm just having some fun. I'm creating a function kind of like I would be doing in 3D Calc Plotter, except I'm going to do it a little differently. And all I'm really doing is I want to be able to drag this guy around a little bit, so I'm locking him in. Don't really pay much attention to that. I just don't. It's not a big deal. What I'm going to do is drag these down. And then I'm going to show you something a little different, because oftentimes in Excel, we think, I say we think, maybe you don't think, maybe you do, maybe I don't know, whatever. But sometimes we think about numerical things like this, differently than we think about what we do in, what's the word I'm thinking about? In sometimes when we do calculus, we think, all right, there's going to be solid answers, and we're going to solve it out, and isn't that great? Okay, cool. But in the real world, we get a lot of, data, right? So sometimes we just get data. We don't actually get a formula. And sometimes we get a formula, but it's kind of hidden. So, but we will see a lot of times, we'll go in and we'll see like, oh, look at that. What do you notice right there? Well, this dark red right here is a definite low spot. That's a definite low spot right there. And of course, we got some high spots here, and if we'd have kept going out of ways, would things have changed? Maybe. And it's that idea of being able to graph things. Now, where have you seen something like that before? Well, if you're like me and you're into cars, you will have seen fuel mapping. Okay? And fuel mapping, one thing that's kind of cool for is the idea that, what you need to do is set up your vehicle so that it keeps the air-fuel ratio as close to stoic, kind of, as you want it to be, as you need it to be. There are times when you're really just mashing the engine and driving it hard that you want it to be rich. You want to have more fuel than you do air, quite a bit, to protect the engine. And there's other times when you're just kind of loping along, you're not working the engine real hard, you're not working it very hard, then you can lean it out and you can actually get better fuel economy. Okay, so if you know your chemistry, 14.7 to 1 is stoic. That's perfect, basically. And so then up here, anything greater than that is lean. It's obviously colored red because that would be a problem. It'd be kind of weird though if you're running at say 4,500 RPMs but had low load on the engine. That'd be kind of weird. Probably not going to happen very often. Anytime you get a high load on the engine, you want to protect the engine and make it go rich. So that's why it's coming down and across. You want to protect the engine, so you run it a little richer. This is that same idea, okay? And you can kind of look at it and go, oh yeah, I see what's going on here. Very similar process. It's a function of several things: speed, load on the engine, a variety of other inputs that kind of come together to create the idea of load on the engine. And they're functions of more than one variable. And what's kind of neat about it is it allows you to kind of visually go, oh yeah, there it is. And in fact, you can actually graph them and see kind of where they are, because then there's your RPM, there's your volumetric efficiency, and there's your load. And then, so then you can just talk about that. And so this is not a graph of air-fuel ratio. It's volumetric efficiency, where you're most efficient when you're running your engine. Lots of different things you can do with those. But again, in this situation, it wouldn't necessarily be, a lot of times it's not exactly a graph or an actual formula. A lot of times it's more the idea of this is raw data that we're getting, okay? And so you can tweak this and tweak that, and then the computer will come back and say, this is where I am. This is what I'm reading as far as air-fuel ratio. And you're like, ooh, no bueno. Let's throw some more fuel at it. All right, see what that looks like. Oh, okay, cool. And it's not a, hey, if I do this, this, and this, bam, that's exactly what I'll get. Formula-wise, sometimes you're going to have to collect some data. And again, we do this kind of stuff all the time in terms of where one thing is a function of several other variables. So in 11.1, you're getting comfortable with it, the idea of level curves, and then just getting comfortable with the graphing of them. And we talked a little bit about domain in 11.1. Now in 11.2, we're going to see, well, what happens as the domain gets kind of weird. In other words, we've talked about limits. All right. As you approach a value that does not exist, we've talked about that a ton. Are you approaching a hole? Is it an asymptote? All these things. Well, guess what? There's a three-dimensional version of all that stuff too. And the idea of limits, what are we going on with that? We're going to talk about that as well. Going to come at it from several different points of view. And then once we get past that, then 11.3 is all about derivatives. You're like, well, why do derivatives follow limits? I don't know, because derivatives are limits. That's right. And then number 4, you're going to do, wait, as soon as you learn derivatives, what did you do? You created a tangent line. That's right. But in Calc 4 here, this class, we don't do tangent lines. We do tangent, wait for it, tangent planes. That's right. And will you do linear approximations? That's right. That's right. What? That's going to be easy. That's right. And then you're going to get into the chain rule. Oh, you remember the chain rule? Same thing in 3 dimensions. It's just a little different. And then 11.6 is the gradient and the directional derivative, which is a lot of fun, I think, one of my favorite chapters. And then in 11.7, you get to do maximums and minimums, which, again, is yet another aspect of Calc 1 when you did derivatives. And so keep that in mind. Everything we're doing in this chapter, well, all of this class for that matter, is taking what we learned in Calc 1 and 2 and then taking it to another level. Okay? So again, in section 1, I do not try to draw these suckers by hand. Okay? When I was a kid, we had to try to, okay, let's see if I can sketch this out. Oh, yeah, I think that's what it looks like and whatever. And no, you had to take the XY trace and the XZ trace and the X and the YZ trace, and you try to combine those 3 flat drawings into one 3D thing. Good luck. I can't do it. And I would never ask that you do it either. Okay? All right, good enough.